Okay, so first, about the class test, it went reasonably well as far as your performance was concerned. Um, I don't exactly remember, but the score, mean score was somewhere around 7, which is okay, 7 out of 10, that is, once you scale everything up, uh, which is not bad. Most people did score somewhere between 7 and 8. Two people scored 10, but most were somewhere in that range. As always, some people did badly, some people did well. That's sort of, and if you look at the distribution curve, it looks rather like a neat Gaussian, which is not bad at all. But what I found rather strange is that the one question which most people messed up on, which of course was a diode doubler question, was one for which the answer was given to you in VLearn if you're just scared to open the. I'm not sure whether people even read the discussion forums, except for the people who are asking the questions. Because if you're scared to read it, you would find that the graph depicting the result was right there in VLearn, the graph which I had given a couple of days ago or a few days ago, and then Kulpahol had asked a question in which a very similar graph was already given. Could have just read off the result from the graph. You didn't have to do anything. So either you could have argued out the result, which is not that easy. That was meant to be a difficult question. But the reason why it was an easy question in the end was that the answer was right there in VLearn if you were just scared to look. So I'm not even sure whether people understand that now. That's what I need to know. Once I tell you that the answer was there, do you realize what I'm talking about? I'm talking actually about this one. Let's see. We'll go to the discussion forum. Am I presenting my screen now? That is, I hope you can see. So if you take a look at the discussion forum, one of the last few messages, in fact, this is the graph for the voltage doubler. Which are given, asked you to look at, and you could actually zoom in, or by any means you want it, just take a look at what's happening at the very beginning. So this is the first half cycle from here to here. And if you just, you could have zoomed in further and just read off what's happening at which thing. So if you just had read it earlier, which I'm pretty sure most of you haven't, you would have known that the answer is given to you in here anyway. So apart from that, does anybody have any questions? Did you get time to take a look at the last video which I put up on how to use SciPy to solve the differential equations? Does anybody have any question on that? None? Okay, if nobody has any questions, then I'm going to move on to a new topic. So please stop me before that.
Sir?
How was the marking done? The answer is the simple way in which you would mark multiple correct answers. Depending on how many choices you get how many correct choices you get in proportion. If you get the wrong choice, there was only one wrong choice, but if you get that, you get 0. That's a standard rule for all multiple correct choices. Yeah, so somebody was asking a question. Yeah.
So in the video of the transistors, I did not understand the connection between the last two circuits.
You mean at the very end, right?
Yes, sir.
Okay, let me just quickly go a bit further back from that. I'm not sure whether most people have watched that video by now, but even if you haven't, basically, so I'm assuming everybody is familiar with transistors. I'm hoping everybody has had time to watch the transistor video, because I've slowed down on the videos a bit for the simple reason that everybody has to be caught up by the end of this week, because otherwise you're going to get completely lost by the time the next week is going to come around. When we go on to more and more computer circuits, it's going to be very, very difficult. Take it from me. But anyway, I'm pretty sure most of you, even if you have not seen the video already, would know that this is basically how a transistor sort of is schematically represented. You have, say, for a PNP transistor, you have P-type region, two P-type regions. So this is a schematic of a PNP transistor. This is a schematic of an NPN transistor. The only difference is in one you have a N-type bread, N-type meat and P-type bread. In the other you have P-type stuffing and N-type breads. That is the two sides of a sandwich. But the basic idea of how it works essentially is can be thought of like this. Okay, I'm skipping over all the details that are there in the video, like the fact that the emitter and the collector, which are these two sides, are really not identical despite what the picture may look like. The emitter is very strongly doped and very small. The collector is lightly doped, much, much larger, and so on. But if you think of an NPN transistor in action, the basic idea is that at least in the active mode, what you do is you reverse bias the base collector junction, which means you make the collector positive and the base negative. That's what you want to do here. The collector base voltage has to be positive. That is for the NPN transistor. For the PNP transistor, this bias would just reverse. The collector base junction would still be reverse biased, but because then collector is P and emitter base is N, VCB will be negative for the active mode for a PNP transistor. For an NPN transistor, I'm going to stick to NPN transistor from now on. This is basically what you're going to have. And in the active mode, what you do is you forward bias the emitter base junction, which means, again, for an NPN transistor, emitter has to be negative compared to the base. That's how you get a forward bias. So VEB is to be 0, is to be less than 0. Okay? And the basic idea of how it works is basically like this. When you forward bias the emitter base junction, a huge number of electrons from the emitter get into the base because the electrons are being pushed by the forward bias into the base. And usually what happens in a PN junction, if you just had a PN and not a PNP or an NPN, if you just had a diode, then when the electrons enter into the from the N side to the P side, then in the P side the electrons would basically recombine with the holes they encounter. But when they recombine with the holes they encounter, that means effectively what happens is that the P side becomes negatively charged, but that charge will not stay because you will not have accumulation of charge. Any charge built up anywhere is energetically unfavorable. So what will happen ultimately is the electrons are going to be pushed out from, so this is basically what I'm talking about. If you have an NP junction, electrons go in, they recombine with holes, but this makes the whole thing negative. And that means some electrons are going to be pushed out from the wire on the p side. Of course, electrons being pushed out is the same thing as current flowing in. But that's essentially how the current works. It's really not the electrons which cross over the barrier, cross over the junction. That gets pushed out immediately. The electrons come in here, they recombine with holes here, and as a result, electrons are pushed out in the long run. It's just like in a wire, current travels very fast, but that doesn't mean that the electrons travel that fast. Electrons travel a lot more slowly compared to the current. But that's, again, you must all be familiar with this analogy with water in a pipe. When you have a pipe full of water, when you pour water in on one end, water comes out of the other end almost immediately, right? It's not as if this water which you poured in one end traveled all the way through the pipe and went out the other end. This water pushes the water next to it, that pushes the water next to it, and that pushes the water next to it, and this wave which travels through the pipe rather fast and makes the water come out at the other end. A very similar thing happens. So the reason why I'm saying this at this stage is that I have to contrast this with what happens in an NPN case. A lot of electrons come in from the emitter to the base, but because the base is deliberately kept very thin and very lightly doped, two things happen. First, there are very few holes to meet those electrons, and second, the base being very thin means the electrons get only very small time to spend there, because the reverse bias which is there between collector and base is now aiding the electrons to move into the collector. So basically, most of the electrons which are injected into the base, they get carried through, they get pushed into the collector. Okay, that's basically how the transistor works. That's a primary mode. Of course, there's another thing that can also happen, which is you can get current flowing through this junction, NP junction, right? Which in the active mode will be rather small, because in the active mode this junction is reverse biased. But when these the electrons come in here, they will also be pushed through. Much of it will be pushed through. A small fraction will recombine, and the recombining fraction is what gives rise to a base current. So basically, the whole idea is, in an NPN transistor, electrons are pushed from the emitter into the base, and they're almost immediately swept out into the collector. Very few recombine at the base to form the base current, right? That's the way in which a transistor works. Of course, if you really wanted to be very precise, you would also have to worry about minority carrier currents and other small factors. But most of them are sort of very small, and we can ignore most of this. Okay, are you with me so far? I hope you are. So this basically is what I described in that video. So I'm just giving a recapitulation in the hope that people who have not had time to watch the video can, and there are quite a few, by the way, I can make that out. But I don't know who you are, so I can't really specifically say who has watched the video and who has not. We are not that much of a big brother as yet. But now, what this actually tells us is that you can sort of mimic this behavior of the transistor by a model. Now, if you have an NPN junction, the first thought would be NP, well, that looks like a diode. It looks like a diode like this, right? NP. And what about the PN? That also looks like a diode. Fine, so this essentially looks like two diodes back to back, the emitter on this side, the collector on this side, and this point is the base. So this is a sort of very simple-minded model of what a transistor can be like. Except that this model doesn't work. Why doesn't it work? It doesn't work for the simple reason that, of course, if this were correct, then there would be no current ever from the emitter to the collector, because either this diode or this one of the two would always be reverse biased. Okay, so no current will be flowing in. Now you might argue that okay, you have seen diodes placed like this, diodes placed back to back in circuits. They were the limiter circuits, which I remember only gave you an output between minus 0.7 volts and plus 0.7 volts, if you remember the diode videos. That's true, but that's really not what we want here. And that's not what happens in a transistor. The major difference between the actual transistor and this model is that in the transistor, the two P's are actually the same, right? That means what happens is the current which can flow here, we call that IED, which is the D stands for diode, E stands for emitter. So IED just stands for the emitter diode. Okay. Now this current is actually pulled almost completely. By the way, the current actually is this way. That may be slightly confusing, but remember in the NPN transistor, what flows, the picture we drew here of electrons flowing. But what flows are electrons, right? They're negatively charged. So the current really is primarily this way. And what we say is, okay, most of this current is pulled into the collector. So essentially whatever current flows here, almost the same current is forced to flow in the collector, but almost the same. This alpha F is of the order of 0.9, could be somewhere between 0.95 and 0.99. So almost all of IED gets to flow through the collector. And similarly, the current that you have here in this other diode, which you call ICD, is also pulled to the emitter, and you call that alpha R ICD. So let me just draw this a bit bigger so that in the NPN transistor you have the emitter diode, the collector diode, and the base, and you have two. This is of course a model. This is really not the actual transistor, but this is effectively what the transistor does. So you have two current controlled current sources, IED, this has the current control source, which is alpha F IED, alpha R ICD. So this is your this I, that's not IE, I should have really labeled just the terminals. The terminal E, this is the terminal C. Of course, by convention, the current flowing into the emitter is called IE, the current flowing into the collector is called IC, the current flowing into the base is called ID. Now this is just one convention which is used in many places, but not always. Some books use the actual direction of the currents, but then of course they will have to use different conventions depending on whether you have an NPN transistor or a PNP transistor. This is just one uniform convention that we use. So all this is just background for what is going to come, and this is background for the question that was asked. This of course is what is called the Ebers-Moll model of the transistor, which is a reasonably good model and describes most of the behavior of the transistor. Now, depending on how accurate you want your transistor model to be, you may want to add more terms to this and bring in more physics, more of the device physics here to understand what the transistor will do, or you can simplify this further. For most practical applications, the Ebers-Moll model is more than enough. Very often we simplify this further. And that was what the question was really about. Okay? The question was essentially about how would you sort of simplify this model if you know that the transistor is in the active mode, which, just to remind you, means base emitter forward biased and the collector base reverse biased. That's how you actually connect the thing. Okay? So if you have this as your model, and then you know that the collector base junction is reverse biased, so what can you do? You can first of all say that ICD will be very, very tiny, right? Because the junction is reverse biased, there's going to be hardly any current there. Okay? Is it fine? Somebody has to be responding, otherwise I don't even know whether I'm still connected. Okay?
Yes, sir.
Okay. So, at least for the active mode, we can forget about this. This diode, we have, okay, so basically what I'm now going to do, I'm going to replace the diodes by their effective circuits. So what is the diode like when it's in reverse bias? It's like an open circuit, right? So because the diode is like an open circuit, you can simply forget about the ICD on this side, which would mean that you just have a current source here. You have two branches here, the current source and the diode. The diode is open, you just have the current source. And on this side, by the way, the moment this diode goes out, that means there's a current through the diode, then this current source, which is of course proportional to that current, is also no longer delivering a current, right? Because ICD is now 0. At least in this approximation, this is of course an approximation, but this is a pretty decent approximation. Under this approximation, alpha or ICD you can simply ignore. So if you are ignoring that, what you have is something very simple. You just have one diode, one current source, right? And now I can even do better than that, because what is this? What is this diode here? The IED. It's of course forward bias, right? So let me remind you that when we talked about a diode, the real diode, what was that equivalent to? It was equivalent to an ideal diode and a series resistance small rd and an opposing voltage V gamma, right? Is it okay?
Yes, sir.
Okay. So what do I do now? What I can do is I can replace this diode here by this thing here. But also, since I know that this diode is forward biased, I can drop the diode by replacing it with a short. Is it okay? So what I can do is I can put a RD and the volt, and but I have to be careful about this, about the polarity. This diode, this battery is supposed to, this effective battery, the cut-in voltage, is supposed to oppose the diode, right? So that only when the forward bias exceeds V gamma do you have real forward bias. So in this case, it's going to be like this. The diode was pointing this way, right, opposite to this side. So the battery here would also have to be switched. Minus on this side, plus on this side. And also, for most practical applications, small RD would be way, way small compared to the resistances that you connect. If you remember, small RD we worked out for the diode, it was around 26 millivolts by the current. So in this case, the current would be IE, right? The current flowing into the emitter. And if you take the ratio for typical milliampere order or tens of milliamperes for IE, then you get a few ohms for RD. Whereas most resistances in a circuit are of the order of kilo ohms or hundreds of ohms. Which means for all practical purposes, we can actually ignore the RD as well. So we will just be left with the V gamma. And the only other thing now is this, of course, this current source. If you remember, the current source was pointing this way. It was currently the same way as IED, right? But its value was alpha F IED, pointing this way. But how is IED related to IE? Well, if you look at this particular node, you can easily write down the current law equation, right? IE goes in, IED also goes in, and if I want to be fully precise, I talk about the full model, then minus alpha R ICD goes out. So net current into the node is given by IE plus IED minus alpha R ICD, and this has to be 0. Kirchhoff's current law, nothing else. Okay. So IE and IED are related to each other by IE equals minus IED plus alpha R ICD. But in our simplified model, that was for the full Ebers-Moll model. In our simplified model, there is no alpha R ICD, which means our IED is actually just minus IE. So saying that it's alpha F IED flowing this way is the same as saying it's alpha F IE flowing the other way. Simply because IED and IE are negatives of each other. So is everybody with me so far? Or is there any confusion about this? Let me just try to do one thing. At least let me try to not obscure the entire screen with this, so that I'm sorry that will make it more difficult for you to see things. However, that way I can at least keep tab as to whether I'm still connected or whether I've just been knocked out. Okay. So if everybody is with me so far, this is what we have. In the active mode, I can approximate the Ebers-Moll model. By the way, the Ebers-Moll model is already an approximation. It's a simplification of the actual transistor, but it's a higher level approximation. But in the active mode, what you can do is you can simplify it further and replace it by this. Emitter, then you have the base, and you have a current of alpha F I. So by convention again, IE and IC are going in, IB is also going in. So is this particular part clear to everybody, or does anybody need any clarification on this? I'm assuming this was not the question, right? The question was about the next part. Or did you need a clarification about this as well?
No, sir, this is okay. I was talking about the next one. Okay,
right. So now notice that this is just one way of looking at this circuit, and this is a very simple result. Ultimately, the transistor essentially ends up looking very simple. By the way, this is the active mode in which the transistor is being used. When you use the transistor as an amplifier, which is its most common usage, or one of its two most common usages, the active mode is usually what you use it as. So, although we will see more complicated models for the transistor later on, after all, we did learn the H parameter equivalent models long time back, and we will have a good occasion to use the H parameter for the transistor. But very often, just using this is good enough. You can actually model a transistor in the active mode very well with this model. Okay, so it's ultimately very, very simple. In fact, you just have a cut-in voltage and a current source. That's it. Now, however, what does this model really tell you? It gives you a bunch of, it essentially tells you something like this. IC is actually minus alpha FIE, right? Because IC is the current going in here, alpha FI is the current coming in here, and of course the net current coming into this node has to be 0. You know that voltage between emitter and base has to be, from this model, what does it have to be? To go from the emitter to the base, and what do you encounter when you go from emitter to the base? What is the voltage drop? Yeah. How much is the voltage drop? It's minus V gamma, of course. Actually it's a rise, and that's obvious because remember we are talking of NPN transistors in the active mode. In NPN, the emitter base junction is forward biased. That means emitter has to be negative compared to the base. So from emitter to the base is really a rise, not a drop. And that's why you have minus V gamma, which is of course what is captured by this model. Okay, so if you think about it a bit, all this model really is telling you is that in an NPN transistor in the active mode, the emitter base junction essentially behaves like a forward bias diode. And just like a forward bias diode, there's going to be a very small voltage drop across it. How much is that voltage drop? Of the order of 0.7 volts. Now you might ask, why did I ignore the small RD and not ignore the 0.7 volts? The answer is simple. Small RD, as I explained, is typically of the order of ohms, and that's much smaller than the other resistances in the circuit. Whereas VEB of 0.7 volts may not be very much smaller than the other voltages involved, because the voltages could be a few volts, 2 or 3 volts even. Then you cannot ignore 0.7 volts and expect to get a good result, right? Which is why we are not replacing the forward bias diode by a short, which would have been the ideal thing to do. But we are replacing it by just an opposing voltage of V gamma. And apart from that, all that you have is basically the statement that whatever current is flowing into the emitter gets pushed onto the collector. Almost all of it, except that there's this alpha F factor here, which is nearly 1 but a bit less than 1. So that's how efficient the collector is in collecting the electrons which went into the base. Okay. Now, this is of course this is perfectly all right, and there's no need to look further. This is a very, very simple model. Whenever you have an actual transistor connected to your circuit, you can replace the transistor by this, and you can easily calculate various results for this. Then after that, notice that once you do it for a real transistor circuit, what happens? In the transistor circuit, you have this non-linear circuit element, the transistor, which has this complicated behavior which we tried to describe so long. But after you replace it by this equivalent, you end up with a circuit which just has some batteries and a controlled current source, right? And you know how to handle controlled current sources. You can do calculations with that very easily. We have already done several calculations in the first few worksheets, right? Where you had controlled sources. And this is really why the control sources are so important, that many of these nonlinear devices actually are very well modeled by control sources. So if you know how to calculate using control sources, you know how to manipulate these complicated calculations. Okay. Now, having said that, the other version of this, the same model, exactly the same thing, not a different thing, exactly the same thing can also be presented in a slightly different manner. A slightly different manner is here. Let me just put it this way. What is this battery doing? The sole job of the battery essentially is to establish a voltage difference between the emitter and the base, right? That's all that the battery is doing, right? So what is it doing? It's making the base higher in voltage than the emitter. By how much? By V gamma, which is around 0.7 volts. So could you achieve this by connecting the battery somewhere else? You could of course do that. You connected the battery here. The same battery. Wouldn't it have exactly the same effect? Would it or would it not have the same effect as the battery here? Or what is the job of this battery? The battery is to establish a voltage rise from this point to this point, which is the base, right? So it essentially makes the base higher than the emitter. What does this battery do? It makes the base higher than this point, but this point is the emitter, right? If you connect a short between 2 points, they're essentially the same point. So when you place the battery here, all that it does is it does exactly the same thing as before. It again gives you VEB equals minus V gamma, right? Is that okay?
So if you place the battery there, it will also affect the VCB voltage.
Will it? First of all, realize that VCB, realize one thing, how do you calculate the VCB voltage? If you here, for example, if you went from the collector to the base, you would have to go over a current source, right?
Yes.
Now, when you go through a current source, you have no clue how much the voltage drop will be. That voltage drop will be established by other circuit elements. A current source, this is something which is very, very important and something which I'm pretty sure is difficult to appreciate for the simple reason that you have not dealt too much with current sources before. But current sources tell you, if you have a current source between 2 points, that will obliterate all information about the voltage difference between those 2 points. That doesn't mean, by the way, I don't mean, of course, that there is no voltage difference between those 2 points, or you cannot find the voltage difference out. All I mean is, to find out the voltage difference between those 2 points, you will have to rely on other circuit components, whatever else is connected to it. The current source is a pure current source, whether it's a direct kind or a controlled kind. A pure current source, by virtue of being a pure current source, allows any amount of voltage, any voltage across it, but drives the given amount of current. If you think about it, it's not very difficult to understand. You know the pure voltage source, right? How much current flows through a pure voltage source? Suppose I have a battery, say I have a 6-volt battery. How much current flows through it?
So it should be infinite because there is no resistance.
No, that's really, of course, not true, because if you have a 6-volt battery just sitting in your tabletop, there's no current, right?
In open circuit, there is no current.
Even when you put a resistance across it, the current is not infinite. Only if you, strictly speaking, put a zero resistance across it, which would be a very stupid thing to do. One of those things they should come with a please don't do it at home kind of warning. Because if you really forget an ideal 6-volt battery, if you took a 6-volt battery, even a real one with some internal resistance, and you connected a short across it, that's one sure shot way of starting a fire or at least burning your fingers. Okay. But the point is, how much current a 6-volt battery will deliver will depend not on the battery. It will depend on what you connect across it. If you don't connect across it, it will deliver zero current. If you connect a 1 kilo ohm resistance across it, it will deliver 6 milliamperes. If you connect a 1 ohm resistance across it, which is a bad idea, it's going to deliver 6 ohms. Okay, sorry, 6 amperes, which might be very convenient if you want to burn things up. But the whole idea behind an ideal voltage source is an ideal voltage source can drive any amount of current and yet maintain the same voltage between the two ends. And that is something which you all know. That's something which you have been familiar with since you ever saw an ideal battery in, say, class 10 or 11. Okay? An ideal current source is something you have seen less often, but you have to realize that when you have an ideal current source, the voltage drop across the two ends of an ideal current source can be anything. The only thing that the ideal current source maintains is how much current flows through it. That's maintained. That's a fixed amount. Or if it's a control source, of course, it depends on whatever other thing is controlling it, but it does not depend on the voltage drop between its two ends. Once again, if you think of the voltage source case, It's not correct to say that I can't know how much current will flow to the battery. I can know how much current through the battery will flow to the battery if I know what is connected to it. It will depend on the other circuit elements. Similarly, here I will know how much current will flow through a current, how much voltage drop will be there across a current source. I know what else is connected to it, right? So why am I saying this? I'm saying this simply to sort of drive home the fact that putting the battery here will really not tell you much about VCB, because in both cases, both here between the collector and the base, you have a current source. In this model as well, in this version, between the collector and the base, now you have a battery and a current source, right? But the current source, frankly, only maintains a given current through it. In this case, it will maintain a current through it which has to be the same current as alpha F IE, because I do not want the equation that I had, that IC is minus alpha F IE, to suddenly go wrong, right? That equation has to be still correct. But I want in this model to express this in terms of IB. But that's easily done, because IC is minus alpha F IE is the same as plus alpha F IC plus IB, right? Notice IE, IB, IC are three currents going into the transistor. Since the transistor cannot accumulate charge, the net current going into it has to be zero. Again, Kirchhoff's current law. So IE is minus IC plus IB, and if I put that in there, I simply get IC is alpha F by 1 minus alpha F into IB. It's not a new equation, it's the same equation as this one. And alpha F by 1 minus alpha F has a name. It's called beta F, or just plain beta. In this model, of course, why did I have this F for forward and R for reverse? F was pulling from the emitter to the collector, R was pulling from the collector to the emitter. But in this particular model, once I have simplified, I don't have the alpha R any longer. So I may even just drop the F and R designation. I can just say beta. Beta IB. Notice that this circuit and this circuit gives you exactly the same relations. This one tells you IC is minus alpha IE. This one tells you IC is minus beta IB. Okay, I must have messed up somewhere. I have messed it up. The arrow here should be pointing the wrong way. I'm not sure whether I messed it up also in the video. You had better make sure that whether I have or have not. IC actually is beta I plus beta IB, and that's what the arrow should be pointing at, away from the collector junction. A beta, of course, is alpha F by 1 minus alpha F. So the point is, this model is a decent approximate model for the transistor when it's in the active mode. This is a decent model for transistor when it's in the active mode. Again, what is the difference? Frankly, there is no difference. These two models say exactly the same thing. What does this model tell you? It tells you, what information does it give you? It tells you that the emitter base junction has a voltage difference. It tells you the current flowing in here is related to. Notice one thing, by the way, this is also important perhaps. Notice that the battery here tells you nothing about the current flowing in, right? Do you have any clue how much the emitter current is from this model? From the fact that there is a battery here, can you tell me how much IE is? Yes or no?
No.
You can't, right? Because a battery will carry whatever current you give it. An ideal battery in particular, without any internal resistance, will always, okay, even a non-ideal battery will carry whatever current you give. The only point is this voltage will depend on the current you give. An ideal battery will have the same voltage across its two ends, no matter how much current you give. So that is again not to say that we cannot find out where IE is, but that will depend on what else is connected to the circuit. Okay. Similarly, on this side, the current source is given. This tells me that the current flowing into this node, which is minus IC, has to be alpha f IE. It tells me nothing about the collector to base voltage drop. This current source is actually connected directly between the collector to the base. But the current source has no information whatsoever about the collector base voltage. That again does not mean that the circuit can have any collector base voltage. That depends on what you connect in the circuit. Okay, is my point clear? And if you think of the two pieces of information this gives us, it gives us an information about the emitter base voltage, does not tell me anything about the current. So I don't care whether you have moved the battery from here to here. That doesn't change anything that way. And this one tells you how much current is flowing into this node. This one also tells you how much current is flowing into this node. It's just rewritten involving IB. That's it. Okay, let me just point out why this is useful. Because in a circuit, let's just use this in a circuit and see how we can sort of make some conclusions, draw some conclusions about it. Let's talk of this circuit. Oops, maybe what I will do is I will move on to the next page and draw this bigger. So I have an NPN transistor connected to this circuit. This is the base emitter junction. By the way, I've said all this in the video, but for those who have forgotten or have not taken a look, the arrow is always in the emitter lead, and it always points in the direction in which current will flow in forward bias. So because it's an NPN transistor, the arrow is in the same direction as in the PN. The diode would have looked like this, right? That's of course an arrow from the P to the N. So that's the same as this arrow here. Now I need to forward bias this junction, of course. So in order to forward bias this junction, I have to make this negative. Let's say I put in a 3 volts battery here, and I put in a, let's just say 1 kilo ohm resistance in series. Remember when I said this in the video, I just showed batteries across the emitter base junction, but I also said this. Nobody connects batteries across a junction. That would be disastrous. You would end up with way too much current and you would end up burning the circuit. The battery there was just to show which way the biasing is. But in a real circuit, you would actually put a battery only in series with a resistance. So that's what we have done here. On the other hand, I want to reverse bias the base collector junction. That means I want to make this positive. So let's say I put in a 6 volt battery here. I'm just making up these numbers. And let's say I've put in a 500 ohm resistor, half a kilo ohm. Okay. Now I want to analyze what this, what currents and voltages will flow under the active circuit connection. These are basically before. This is of course. By the way, if this is going to be an amplifier, this would need a signal, right? An amplifier would have to amplify a signal. Where is the signal in this circuit? Any idea?
The 3 volt battery.
No, that's not a signal. That's the point. Okay, this is biasing. The point is you want to get the transistor. A signal would typically be an AC signal which goes positive, negative both. Now, if you want your transistor to be in the active region, you would not put in a sinusoidal signal onto the emitter, right? Directly. Because if you did that, only for one half of the cycle will the emitter be forward biased. For the other half of the cycle, the emitter base junction will be reverse biased, which would mean that you are putting the transistor in the active mode only half of the time. There are, by the way, transistor amplifiers which work under such conditions, but the most common transistor amplifier does not. The most common transistor amplifier tries to ensure that no matter what signal you give, the emitter base junction is forward biased throughout. You are working in the active region throughout. Okay. What that means is that whatever signal you give will be on top of some voltage which is already there. Let's just say I have 1 volt signal which goes from plus 1 volt to minus 1 volt. What I want to do is I already have a 3 volt signal somewhere. On top of that I give this additional signal. Do you get my point? I do not want the transistor to go out of the active region. I want it to always have a forward biased emitter base junction, which is why there is no signal in this circuit, by the way. This circuit is what is called a biasing circuit, which establishes voltages and currents in the circuit before you give a signal. A signal is given on top of this. Okay. So what we are studying right now is how to bias a transistor and get what are called quiescent point or steady state values. And this is where I would urge all of you to go back and take a look at the small signal 2-port network video once again. The Z parameter, Y parameter, in particular the H parameter. Because if you remember there, what we said is there are some steady values and you have fluctuations around those steady values. It is the fluctuations for which you actually write down the H parameters or Y parameters or whatever you want. At that point of time, people are, of course, the one example that I gave there had steady quiescent point values of 0. So there was some confusion as to what was this fluctuation I was talking about. But now, when you apply the H parameter model or what you would call a small signal AC model to the transistor, you would actually use the fluctuation from the quiescent value. These are just the quiescent values and steady state values that we are setting up right now. Now, just quickly, if you were to replace the transistor with this equivalent circuit, so 6 volt, 3 volts, wait a minute, I think I've got this wrong. I drew it wrong. Or rather, I drew it. Okay, what I drew a while ago for this battery is a typical kind of answer which people would give in a Viva, which could go either way. I didn't draw a proper battery, I just drew half of it. So it's like I'm pretty sure most of you have watched that Amitabh Bachchan movie, right? The one in which he was talking about how big the victim was. He was standing witness. I forget which film that was. So he was telling the judge this: the victim is this tall, and then when told that the victim is a cock, he just said that dusra haath to nahi dala. So put the other hand below. This is essentially what I was doing. Remember, we had a battery, so you have to have an equal number of positive negative ends on this side. You want this 6 volts to point this way. That is why the reverse. Sorry, I had it both ways last time, but this is wrong. Right? I want this to be reverse biased. I want this to be forward biased, so this side N is fine. This to be reverse biased, so this side has to be P. So what I need is I need to get rid of this one and this one. Okay, so this is plus minus. Okay, but what I really meant to talk about is not that. If you were using the base, using the first model, which is this one, what I would do is just connect the battery here, emitter based battery, 0.7 volts, let's say. So this is the emitter, the 0.7 volts between emitter and the middle junction. And alpha, let's say alpha is approximately 1. So this is, let's put this at almost I. So now, with this equivalent circuit, can you tell me how much is the current IE going to be? And IE is this current. How much is it going to be? You just look at this loop. It should be obvious, right? How much is the drop in this loop? You have a 3 volt rise and a 0.7 volt drop if you go this way, right? So you have a 2.3 volts and there's a 1 kilo ohm. So IE will simply come out in minus 2.3 volts. Okay? Yeah? And what about minus 2.3 milliamperes? That's of course stupid of me. Can't be volts, right? It's 2.3 volts by 1 kilo ohm. So minus 2.3 milliamperes, minus sign simply because by convention emitter current is always into the resistor. Here the current of course flows out. And so how much is the current here?
Almost the same.
Almost the same. So here also IC, which is minus alpha, minus IE almost now, is going to be 2.3 milliamperes. So now can you tell me how much the collector to base voltage drop is going to be? That's the last part of this class. How to find the collector to base voltage drop? You go from the collector to the base and add up all the voltage drops on the way, right? That's what you do. However, and this is very important, if you go this way, you can go from here to the base, but on the way what you encounter is a current source. Now you have no clue how much the voltage drop across the current source is. So as I was saying, the current source will tell you nothing about the voltage drop. Fine, but you can go now that you know what else is connected to the circuit, can go from the collector to the base, not via this path, but via this path. Right? Is it okay?
Yes, sir.
So when you go this way, you can find out what the change is. Okay, by the way, I must apologize and change this one again. I forgot to change this one. Okay, so when you go from here to here, what happens? This is 2.3 milliamperes this way. So 2.3 milliamperes into 500 ohms, that's 1.15 volts, which is when you're going from here to here, it's actually a rise. You're going against the current. So 1.15 volts rise, and then a 6 volt. So find out what the change is. How much is the collector base voltage? So collector voltage is 6 volts minus 1.15 volts. That's of course, VBC. Collector to base is actually opposite of that. Minus 6 volts plus 1.15 volts. Rise of 1.15 volts, drop of 6 volts. Minus 4.85 volts. By the way, this is an NPN transistor. What did I miss? I again messed up the sign somewhere. This is fine. This is positive. Collector to base drop. Collector to base drop is minus 4.85 volts, which means collector is higher than the base, which is fine. Oh, no. I messed up somewhere again. Now this is of course both embarrassing as well as dangerous because it makes the audience think that this is more difficult than it is. It's really not difficult. I just have to get the currents right. I'm having difficulty enough getting the picture to be drawn correct. So that's a nice excuse I have. Let me just draw it correctly now, once and for all. I want the collector to be higher than the base, right? So that's why I drew put a plus 6 volt battery here. Then I have and this is the current that's going to go. So of course if I go from the collector to the base, I'm going to get a drop. How much drop am I going to get? I'm going to get a drop of minus 1.15 volts here. That's a rise, so it should count as a minus 1.15 volts. And then I have a drop again. Oops. Yeah, this is a rise, this is a drop. Okay, fine. I don't know why I am messing this up. This is pretty straightforward. So before I embarrass myself any further, let me just calculate the collector to base drop properly. Here is a rise, that's minus 1.15 volts of drop, and here is a drop, so that's plus 6 volts. There's a 4.85 volts drop between the collector to the base, which is fine.
So in the right section, shouldn't current flow clockwise?
In this section, you mean current should flow this way? That's because of this arrow, right? You're saying that because of this arrow, right? Is that what you're saying?
Yes, sir.
Yeah, but that arrow tells you what? That the current in that arrow is IE. Okay?
I is negative.
IE is negative.
But I got it, sir.
Yeah, this is something you have to be. Okay, I sort of mess this up often enough, so I should not really sermon people about not being careful about this, especially after my display a while ago of messing up simple voltage rises and drops. I should be the last person to actually give you a lecture on this, but you have to pay attention to the signs. So it looks like the current is clockwise. It's not. It's actually counterclockwise, which, by the way, I said that here, right? IE is minus 2.3 milliamperes. IC, again, no, by convention, IC flows in. But IC, remember, is minus IE. Well, actually, it's minus alpha IE. So alpha is nearly 1. So it's plus 2.3 milliamperes. So this is where you get to know what are the voltages at different parts of the circuit, how much current is flowing. So that without any signal being applied. There is no signal here as yet. So this is not amplifying. This is just setting up voltages and currents. So in the next video, we will talk a lot about biasing a transistor circuit, and also talk about then go on to talk about what happens when you put signals on top of that. Okay. But quickly, let me just point out that if I wanted to analyze the same circuit with the other one, it will be slightly more complicated. Not much, only slightly. So in fact, of the two equivalent circuits that we drew, this one is actually more suited when the base is the reference, and this one is better suited when the emitter is the reference point. You will see why in the coming videos and also in the discussion class later. By the way, one thing, next class cannot be held on Friday because I have a very important meeting on Friday. So what we will do is, just for that week, I will have the class on Saturday. I will let you know the timings, but just for that week. And of course, the week after that, I think is the puja break, right? You have an autumn break this time or no? I don't know.
Yes, we have.
You really have one whole week of autumn break?
Yes.
To stay home and do nothing. Very good. Okay. Then, yeah?
Sir, actually, I was confused about that quiz question regarding voltage doubler. Sir, can you please repeat why it will not be Vp by 2 at T? Because the one which you have plotted, is it for was there a resistance connected, or was it ideal?
It was ideal.
Okay.
It was ideal.
Can you just repeat why at T is equal to T it will not be Vp by 2? Because it should rise from Vp by 2 at the instant T equal to T by 2, right?
At T equal to?
At T is equal to T, it should rise from Vp by 2.
No. That's where you're wrong actually. Okay, it will. The point. Okay, unfortunately you asked us a bit too late. So if you can stick around, I have no problem. But I just don't want to sort of run into somebody else's class. But the point really was, if you follow the thing carefully, if this is your input voltage, which rises to Vp at time t by 4, then the capacitor voltage rises to Vp by 2 at time t by 4, which almost everybody got right. Okay. After that, the voltage V2 stays fixed. Why does it stay fixed? Simply because the capacitor, which is here, cannot lose any potential, because any loss of potential would have to be through this, right? And it can't lose loss of potential means loss of charge. It means charge would have to flow against the arrow of an ideal PN junction diode, which is impossible. So the second capacitor is a true peak detector. It will never lose its voltage. It will only rise. What you're wrong about is when does it start to rise? It actually starts to rise before it reaches T. And for that, you have to worry about what happens to the first capacitor. This was the scenario, right? This was your circuit. And at this peak, what has happened is this has reached Vp by 2. This point has also reached Vp by 2. Remember, this diode is reverse biased, so it can carry any voltage across it. After that, what happens? After that, this diode, of course, when this comes down, since this is reverse bias, this diode maintains the voltage across it, so it just comes down from this value. So it reaches 0 before the input reaches 0, when the input falls to Vp by 2, actually. Okay, and then it keeps on going. It keeps on following the input throughout, but then it rises, and this is where, okay, I will urge you to take a look at this more carefully. You will find that it actually rises a lot earlier. Let me just quickly show you one thing. I think this will be easier for you to. Okay, let me just, okay, this was the, let me just zoom in to the first cycle. Okay, so this is your green thing. Okay, T is here. I hope everybody can see the curve, right? Can you see the curves?
Yes, sir.
Okay, the blue is the input signal. Okay. The green curve is the V2. That's the voltage which we are talking about. The orange curve is V1. And the red curve here is the voltage drop across the first capacitor. So if you look at it at the beginning, both the green curve and the orange curve rise together, and the red curve, all three rise together. That's because the capacitors are identical, they both charge up identically, and they go to Vp by 2 when the peak is reached. After that, the diode, the first diode, the one on the left, is still reverse biased. So the voltage drop across it keeps on dropping with the input, drops to 0, and then the diode becomes forward biased here, so that the voltage drop across the diode goes to 0 and stays 0. Now when does the voltage V1 start to, as long as the second diode, the one on the left, oops, not something which you need to see. This is not something I wanted to scare you with. That was not my intention. This is the diode. This diode, as long as it is forward biased, it will maintain this voltage at 0, right? Of course, this is 0, this is Vp by 2, this diode is still reverse biased, so this, of course, does not lose any of its charge. But as long as this is forward biased, this voltage stays at 0. The capacitor voltage keeps on changing with the input voltage. And then, so that's why the capacitor voltage just keeps on dropping with the input voltage. But when the capacitor voltage reaches, the input voltage reaches the minimum value and then starts to rise, that reverse biases the first diode. And so the voltage starts to pick up again. I guess the mistake all of you were making is this, that the second diode becomes forward biased and hence the second capacitor charges up only when the input, oops, let's go back, only when the input voltage becomes positive. That's not true, so it doesn't go all the way here. Once the input voltage starts picking up from its minimum value, the first diode is no longer forward biased, it becomes reverse biased, which means the voltage across it climbs. It climbs. Now, by the way, one thing also is important, it climbs faster than the voltage across than it was climbing before. Why? Because before, both capacitors were charging up. Now it's only this capacitor which is charging up, the other capacitor is still not charging because that diode is still reverse biased. So it goes and picks up, becomes bigger than Vp by 2 before this input hits 0. It will be when this input is minus Vp by 2. And after that point, both of them start charging together. Again, start charging together at the same rate simply because they're identical capacitors. Now, D1 has gone reverse biased, D2 is forward biased, so both are charging together, as in the beginning. So it's really T by 4. At T by 4 is Vp by 2. At T is also Vp by 2. At 3T by 2 is also Vp by 2. But at T, it's not Vp by 2, it's actually more than Vp by 2. So I will just ask you to think about this, and this graph is there. You can write your own program to get the graph. That was the homework anyway, or at least you could use whatever you learned from the homework to figure this out. Or either way, the whole point is the second diode goes forward biased, and that is the important point. If you look at this together, let's see. The second diode goes forward biased whenever this voltage exceeds Vp by 2. And this exceeds Vp by 2 before this Vi is back. Because remember, this was a 0. So from 0, all it has to do is rise by Vp by 2. It doesn't have to rise all the way to Vp. So that happens before this 0 is reached. So at T, which was the last option, the voltage actually is much higher already. You can actually figure out exactly how much the voltage is, assuming ideal diodes. That could be a nice question actually. I'm not sure whether I've been able to explain this to you that well, just because I couldn't put the two things together back at the same time. I should have actually had the circuit drawn here somewhere along with this. I think this you should be able to make out. Rise this together to Vp by 2, then this one falls, waits at 0 until the input voltage starts to rise. Once the input voltage starts to rise again, because the capacitor is at minus Vp by 2, minus Vp, and holds on at minus Vp, it can't discharge now. Because both the diodes are reverse biased. Now the capacitor can no longer discharge. I mean the first capacitor, this one, can no longer discharge. So the input rises, the capacitor voltage stays minus Vp. So this voltage rises. It's actually pretty easy. It's tedious if you have to keep on doing it for cycle after cycle, but getting the behavior for the first cycle is not very difficult. All you have to do is think about which diode is reverse biased, which one is forward biased, and just realize that for a capacitor to change its voltage, it has to have current through it. So if both diodes are reverse biased, it's impossible for the capacitor to change its voltage. That's the situation that happens here. Sorry, not here, here. And for the second capacitor here, all the way from here to here. Of course, for the second capacitor, it's only this diode which is controlling its current. So only this, as long as this diode is reverse biased, this capacitor will hold this voltage. I guess the only mistake that people have made is this one. Forgotten about the fact that that is this voltage which held the forward bias, not the input, by the way, but the voltage here, which decides whether this diode is forward biased. So I will urge you to think about it. If you still find it unclear, we will discuss this at the beginning of the next class. Okay?
Okay.
Just think about it. Just think about which diode is forward biased. It should be pretty easy to figure out. Okay. I think we will call it a day today. Yeah. Let's stop the recording and